815 yen 560 yen 508, 0.1 to 0.3.3 Molding materials. A large variety of molding materials are used in foundries for manufacturing molds and cores. They are molding sand, system sand, backing sand, rebonded sand, facing sand, parting sand. Core sand. The choice of molding materials is based on their processing properties. The properties that are generally required in molding materials are refractoriness. It is the ability of the molding material to withstand the high temperatures of the molten metal so that it does not cause fusion. Some refractory materials are given in Table 3.7. Green strength. The molding sand that contains moisture is termed as green sand. The green sand should have enough strength so that the constructed mold retains its shape. Dry strength. When the moisture in the molding sand is completely expelled, it is called dry sand. When molten metal is poured into a mold, the sand around the mold cavity is quickly converted into dry sand as the moisture in the sand immediately evaporates due to the heat in the molten metal. At this stage, it should retain the mold cavity and at the same time withstand the metallostatic forces. Hot strength. After all the moisture is eliminated, the sand would reach a high temperature when the metal in the mold is still in the liquid state. The strength of the sand that is required to hold the shape of the mold cavity is called hot strength. Metal casting processes 3.25. Table 3.7 Properties of some refractory materials. Material melting point, degree C. Coefficient of linear expansion, 106 yen/degree C. Silica, SiO2, 1710 16.2 alumina, Al2O3, 2028.0 magnesia, MgO, 2813.5 thoria, Tho2, 3059.5 zirconia, ZrO2, 2706.5 zircon, ZrO2. SiO2, 2654.5 silicon carbide, SiC, 2703.5 graphite 4200. Permeability. During the solidification of a casting, large amounts of gases are to be expelled from the mold. The gases are those which have been absorbed by the metal in the furnace, air absorbed from the atmosphere, steam, and other gases that are generated by the molding and core sands. If these gases are not allowed to escape from the mold, they would be trapped inside the casting, causing defects. The molding sand should be sufficiently porous so that the gases are allowed to escape from the mold. This gas evolution capability of the molding sand is termed as permeability. Besides these specific properties, the molding sand should also have collapsibility so that during the contraction of the solidified casting, it does not provide any resistance which may result in cracks in the casting. Casting. They should be reusable and should have good thermal conductivity so that heat from the casting is quickly transferred.
Sand composition. The main ingredients of any molding sand are silica grains, SiO2, clay as binder, moisture to activate the clay and provide plasticity. Besides, some other materials are also added to these to enhance the specific properties of molding sands, the details of which are given in later chapters. Silica sand. The sand which forms the major portion of the molding sand, up to 96%, is entirely silica grains, the rest being the other oxides such as alumina, sodium, Na2O and K2O, and magnesium oxide, MgO and CaO. These impurities should be minimized to about 2% since they affect the fusion point of the silica sands. The main source is the river sand, which is used with or without washing. Ideally, the fusion point of sands should be about 1450 degrees Celsius for cast irons and about 1550 degrees Celsius for steels. In the river sand, all sizes and shapes of grains are mixed. The sand grains may vary in size from a few micrometers to a few millimeters. Shape of the grains may be round, subangular, angular and very angular. Angular. The size and shapes of these sand grains greatly affect the properties of the molding sands, which are explained later in this chapter. Zircon sand is basically a zirconium silicate, ZrSiO4. The typical composition is ZrO2 equals 66.25%, SiO2 equals 30.96%, Al2O3 equals 1.92%, Fe2O3 equals 0.74% and traces of other oxides. It is very expensive. In India it is available in Quilon Beach of Kerala. It has a fusion point of about 2400 degrees Celsius, and also a low coefficient of thermal expansion. The other advantages are high thermal conductivity, high chilling power, and high density. It requires a very small amount of binder, about 3%. It is generally used to manufacture precision steel castings requiring better surface finish, and for precision investment casting. 3.26 Manufacturing technology, foundry, forming and welding. Chromite sand is crushed from the chrome, ore whose typical composition is Cr2O3 equals 44%, Fe2O3 equals 28%, SiO2 equals 2.5%, CaO equals 0.5%, and Al2O3 plus MgO equals 25%. The fusion point is about 1800 OC. It also requires a very small amount of binder, about 3%. It is also used to manufacture heavy steel castings requiring better surface finish. It is best suited to austenitic manganese steel castings. Olivine sand contains the minerals phosphorite, Mg2SiO4, and phyolite, Fe2SiO4. It is very versatile sand and the same mixture can be used for a range of steels. Comparative properties relevant for molding of these various base sands are given in Table 3.8. Clays are the most generally used binding agents mixed with the molding sands to provide the strength because of their low cost and wider utility. The most popular clay types used are kaolinite or fire clay, Al2O3 2SiO2 2H2O, and bentonite, Al2O3 4SiO2 H2O and H2O. Kaolinite has a melting point of 1750 to 1787 degrees Celsius, and bentonite has melting temperature range of 1250 to 1300 degrees Celsius. Of the two, bentonite can absorb more water which increases its bonding power. The clays besides these basic constituents may also contain some mixtures of lime, alkalis and other oxides which tend to reduce their refractoriness. There are basically two types of bentonites, one with sodium as adsorbed ion often called western bentonite, and the other with calcium ion called southern bentonite. Sodium bentonites produce better swelling properties. Volume increases some 10 to 20 times, high dry strength which lowers the risk of erosion, better tolerance of variations in water content, low green strength, and high resistance to burnout, which reduces clay consumption. In contrast, the calcium bentonites have low dry strength, but higher green strength. It is possible to improve the properties of calcium bentonite by treating it chemically with soda ash sodium carbonate. The clay chosen for molding sand should give it the requisite strength for the given application taking into account the metal being cast and thickness of the casting. Normally, the river sand contains a large amount of clay and therefore can be directly used. Table 3.8 Comparison of foundry-based sand properties. Silica olivine chromite zircon color white light brown greenish gray black white brown. Hardness 6.0, 7.0, 6.5, 7.0, 5.5, 7.0, 7.0, 7.5 dry bulk density, lb/foot 3, 85, 100, 100, 125, 155, 165, 160, 185 specific gravity 2.2, 2.6, 3.2, 3.6, 4.3, 4.5, 4.4, 4.7 grain shape angular/rounded angular rounded/angular. Thermal expansion, mm/degree C, 0.018 0.0083 0.005 0.003. Apparent heat transfer average low very high. Fusion point, degree C 1427 1760 1538 1760 1760, 1982 2038 22, O for high temperature reaction acid basic acid. Wettability with molten metal easily not generally resistant grain distribution 2 5 screens 3 4 screens 4 5 screens 2 3 screens AFS grain fineness number 25 180 40 160 50 90 95 160. Metal casting processes 3.27. Water clay is activated by water so that it develops the necessary plasticity and metal casting processes 3.27. Water clay is activated by water so that it develops the necessary plasticity and strength. The amount of water used should be properly controlled. This is because a part of the water absorbed by clay helps in bonding while the remainder up to a limit helps in improving the plasticity, but more than that it would decrease the strength and formability. The normal percentages of water used are from 2 to 8. Besides these three main ingredients, many other materials also may be added to enhance the specific properties. For example, PLE, cereal binder up to 2% increases the strength, pitch of tie net as a byproduct in coke making if used in percentages up to 3 would improve the hot strength, and sawdust up to 2% may improve the collapsibility by slowly burning and increase the permeability. There are other materials such as sea coal, asphalt, fuel oil, graphite, molasses, iron oxide, etc., which are also used for obtaining specific properties. Comparative properties of molding sands with various clays are shown in Table 3.9 below. Table 3.9 Comparison of foundry sand properties with various clays. Sodium bentonite fire clay calcium bentonite silica sand, AFS GFN 60, weight percent 95 88 95 clay bond, weight percent 5 12 5 moisture, weight percent 2.5, 3.0, 2.5 permeability 110, 6108 green compression strength. KPA 76.5, 363.43, 97.22 dry compression strength. KPA 675.70, 468.84, 372.32. 3.3.2 Testing sand properties. The molding sand, after it is prepared, should be properly tested to see that the requisite properties are achieved. There are standard tests to be used which are given in relevant Indian standards, and that of other foundry societies, a list of which is given at the end of this chapter. However, a brief review is made here of the general testing methods. Sample preparation. Tests are conducted on a sample of the standard sand. The molding sand should be prepared exactly as is done in the shop on the standard equipment, and then carefully enclosed in a closed container to safeguard its moisture content. Moisture content. As explained earlier, moisture is an important element of the molding sand as it affects many properties. To test the moisture of molding sand, a carefully weighed test sample of 50 g is dried at a temperature of 105 degrees Celsius to 110 degrees Celsius for 2 hours, by which all the moisture in the sand would have been evaporated. The sample is then weighed. The weight difference in grams when multiplied by 2 would give the percentage of moisture contained in the molding sand. Alternatively, a moisture teller can also be used for measuring the moisture content. In this test, the sand is dried by suspending the sample on a fine metallic screen, and allowing hot air to flow through the sample. This method of drying completes the removal of moisture in a matter of minutes compared to 2 hours as in the earlier method. Another moisture teller utilizes calcium carbide to measure the moisture content. A measured amount of calcium carbide, a little more than actually required for complete reaction, in a container along with a 3.28 manufacturing technology, foundry, forming and welding. Separate cap consisting of measured quantity of molding sand is kept in the moisture teller. Care has to be taken before closing the apparatus that carbide and sand do not come into contact. The apparatus is then shaken vigorously such that the following reaction takes place. CaC2 plus 2H2O AeC2H2 and CaO2. The acetylene, C2H2, coming out will be collected in the space above the sand, raising the pressure. A pressure gauge connected to the apparatus would give directly the amount of acetylene generated, which is proportional to the moisture present. It is possible to calibrate the pressure gauge, or manometer, to directly read the amount of moisture. Clay content. The clay content of molding sand is determined by dissolving or washing it off the sand. To determine the clay percentage, of 50 g sample is dried at 105 to 110 degrees Celsius. The dried sample is taken in a 1 liter glass flask and added with for 75 ml of distilled water and 25 ml of a 1% solution of caustic soda, NaOH 25 g per liter. This sample is then thoroughly stirred. After the stirring for a period of 5 minutes, the sample is diluted with fresh water up to a 150 mm graduation mark, and the sample is left undisturbed for 10 minutes to settle. The sand settles at the bottom and the clay particles washed from the sand would be floating in the water. 125 mm of this water is siphoned off the flask, and it is again topped to the same level, and allowed to settle for 5 minutes. The above operation is repeated till the water above the sand becomes clear, indicating that all the clay in the molding sand has been removed. Now, the sand is removed from the flask and dried by heating. The difference in weight of the dried sand in 50 g when multiplied by 2 gives the clay percentage in the molding sand. Sand grain size. To find out the sand grain size, a sand sample which is devoid of moisture and clay such as the one obtained after the previous testing is to be used. The dried clay-free sand grains are placed on the top sieve of a sieve shaker, which contains a series of sieves one upon the other with gradually decreasing mesh sizes. The mesh sizes are standardized as shown in table 3.10. The sieves are shaken continuously for a period of 15 minutes. After this shaking operation, the sieves are taken apart, and the sand left over on each of the sieve is carefully weighed. Table 3.1. And their Indian equivalents with sizes. US series equivalent, no. ASTM. Mesh opening, mm. Metal casting processes 3.29. The sand retained on each of the sieve expressed as a percentage of the total mass can be plotted against the sieve number as in Fig. 3.21 to obtain the grain distribution. But more important is the grain fineness number, GFN, which is a quantitative indication of the grain distribution. To calculate the grain fineness number, each sieve has been given a weightage factor as shown in table 3.10. The amount retained on each sieve is multiplied by the respective weightage factor, summed up, and then divided by the total mass of the sample, which gives the grain fineness number. The same can be expressed as GFN equals III. MFFSS. Where me equals multiplying factor for the sieve phi equals amount of sand retained on the sieve. 190 80 70 60 50 40 30 20 10 0. 12 20 30 40 50 sieve number. Cumulative. Percentages. 70 100 140 200 270. Fig. 3.21 Sand grain size distribution. A typical example is presented in Table 3.11 for calculating the grain fineness number. This type of sand is normally used in malleable and gray iron foundries for castings which weigh more than 20 kilograms. By the above definition, the grain fineness number is the average grain size and corresponds to a sieve number through which all the sand grains would pass through, if they were all of the same size. This is a very convenient way of describing the grain size, and its value can be expected between 40 and 220 for the sands used by most of the foundries. Though the sand properties depend on both the grain size and the grain size distribution, GFN is a very convenient way of finding the sand properties since it takes both into AC count. Table 3.12 gives the sieve analysis for the typical sands, which may be used for the purposes mentioned. Permeability, the rate of flow of air passing through a standard specimen under a standard pressure, is termed as permeability number. 3.30 Manufacturing technology, foundry, forming and welding. Table 3.11 Sieve analysis. Sieve number multiplying factor, me retain sample phi e.g., retain percentage pi me yen phi 40 32.4955 100 and 50 74.85 50 40 13.972 28 1100 and 2500 and 58.88 70 50 23.95 248 2400 1100 and 97.60 176.986 14 980 400 and 89.0 to 140 102.4955 500 249.50 49.900 1005 150 2569.85. GFN equals 5,100 and 5100 equals 51.50. GFN equals 2,569.85 49.90 equals 51.50. Table 3.12 Typical sand sieve analysis. Sieve number multiplier me sand 1 sand 2 sand 3 sand for retained percent pi me pi pi me pi pi me pi pi me pi. 30 20 120 40 30 33 900 and 91 30 0.6 18 1.2 36 50 40 40 for 1700 and 60 15 600 1 for 56 6 200 and 40 70 50 15 700 and 50 32 1000. The standard permeability P equals VHPAT. P equals VH. The standard permeability test is to measure time taken by a 2000 cub cm of air at a pressure typically of 980 Pa 10 G/cm2 to pass through a standard sand specimen confined in a specimen tube. Fig. 3.22. The standard specimen size is 50.8 millimeters in diameter and a length of 50.8 millimeters. Then, the permeability number P is obtained by P equals VHPAT. Metal casting processes 3.31. Where V equals volume of air equals 2000 centimeters cubed. H equals height of the sand specimen equals 5.08 centimeters. P equals air pressure, G/cm2. A equals cross-sectional area of sand specimen equals 20.268 centimeters squared. T equals time in minutes for the complete air to pass through. Inserting the above standard values into the expression, we get P equals 500 and 1.28 pt. Specimen preparation. Since the permeability of sand is dependent to a great extent on the degree of ramming, it is necessary that the specimen be prepared under standard conditions. To get reproducibly ramming conditions, a laboratory sand rammer is used along with a specimen tube. The measured amount of sand is filled in the specimen tube, and a fixed weight of 6.35 to 7.25 kilograms is allowed to fall on the sand 3 times from a height of 50.8 plus 0.125 millimeters. The specimen thus produced should have a height of 50.8 plus 0.8 millimeters. To produce this size of specimen, usually sand of 145 to 175 G would be required. After preparing a test sample of sand as described, 2000 centimeters cubed of air is passed through the sample, and the time taken by it to completely pass through the specimen is noted. Then from the above equation the permeability number can be calculated. Example 3.5 Calculate the permeability number of sand if it takes 1 minute 25 s to pass 2000 centimeters cubed of air at a pressure of 5 G/cm2 through the standard sample. P equals 5.0 G/cm2. T equals 1 minute 25 s equals 25 1 plus 60 equals 1.417 minutes. Permeability number P equals 500 and 1.285 1.417 yen equals 70.75. The permeability test is conducted for 2 types of sands. A. Green permeability is the permeability of the green sand. B. Dry permeability is the permeability of the molding sand, dried at 105 to 110 degrees Celsius to remove the moisture completely. Strength. Measurement of strength of molding sands can be carried out on the universal sand STRE NGTH testing machine. The strength can be measured in compression, shear and tension. The sands that could be tested are green sand, dry sand or coarse sand. The compression and shear test involve the standard cylindrical specimen that was used for the permeability test. Fig. 3.22 Permeability meter for May assuring the permeability of green sand. 3.32 Manufacturing technology, foundry, forming and welding. Green compression strength. Green compression strength or simply green strength generally refers to the stress required to rupture the sand specimen under compressive loading. The sand specimen taken out of the specimen tube is immediately, any delay causes the drying of the sample which increases the strength, put on the strength testing machine, and the force required to cause the compression failure is determined. The green strength of sands is generally in the range of 30 to 160 kPa. Green shear strength. With a sand sample similar to the above test, a different adapter is fitted in the universal machine so that the loading now be made for the shearing of the sand sample. The stress required to shear the specimen along the axis is then represented as the green shear strength NGTH. The green shear strengths may vary from 10 to 50 kPa. Dry strength. The test similar to the above can also be carried with the standard specimens dried between 105 degrees to 110 degrees Celsius for 2 hours. Since the strength greatly increase with drying, it may be necessary to apply larger stresses than the previous tests. The range of dry compression strengths found in molding sands is from 140 to 1,800 kPa, depending on the sand sample. Mold hardness. The mold hardness is measured by a method similar to the Brinell hardness test. A spring-loaded steel ball with a mass of 0.9 kilograms is indented into the standard sand specimen Prepa Red. The depth of indentation can be directly measured on a scale which shows units 0 to 100. When no penetration occurs, then it is a mold hardness of 100, and when it sinks completely, the reading is 0, indicating a very soft mold. Besides these, there are other tests to determine such properties as deformation, green tensile strength, hot strength, expansion, etc. The details of these testing methods can be found in the references cited at the end of this chapter. 3.3.3 Sand preparation. One of the important requirements for the preparation of sand is thorough mixing of its various ingredients. This is essential to ensure uniform distribution of the various components in the entire bulk of the sand. During the mixing process, any lump present in sand is broken up and clay is uniformly enveloped around the sand grains and moisture is uniformly distributed. Besides manual mixing, equipment called Mueller is normally used in foundries to mix the sands. These are essentially of two types, batch type and continuous. As shown in Fig. 3.23, a batch Mueller consists of 1 or 2 Mueller wheels and equal number of plow blades connected to a single driving source. The Mueller wheels are large and heavy, and continuously roll inside the Mueller bowl. The plow blades ensure that the sand is continuously agitated. The combined action of both these is a sort of kneading action which makes the clay and the moisture uniformly distributed throughout the sand. A continuous Mueller consists of 2 bowls with Mueller wheels and plows such that sand, clay and moisture are fed through a hopper into one of the bowls which after getting mulled moves into the second one and then finally out. Thus, well-prepared molding sand is continuously available for use. It is generally used for large-scale production. 3.3 For molding sand properties. The properties of molding sand are dependent to a great extent on a number of variables. The important among them are metal casting processes 3.33, sand grain shape and size, clay type and amount moisture content, method of preparing sand mold. Fig. 3.23 Batch Mueller. Sand grains. The shape and size of the sand grain would greatly affect the various molding sand properties. The sand grain size could be coarse or fine. Similarly, the grain shape could be round or size of the sand grain would greatly affect the various molding sand properties. The sand grain size could be coarse or fine. Similarly, the grain shape could be round or angular. The coarse grains would have more void space between the grains, which increases the permeability. Similarly, the finer grains would have lower permeability, however they provide better surface finish to the casting produced. The distribution of the grain size also plays an important role. For example, widely distributed sand would have higher permeability than the one with the same fineness number but where all the grains have the same size. Angular sand grains require higher amounts of binder. The round grains would have lower permeability compared to angular grains because of the irregular shape of the latter. The same has been depicted in Fig. 3.24. The grain size also affects the refractoriness. Higher the grain size, higher would be the refractoriness. The purity of sand grains also improves the refractoriness. For example, sand grains with a GFN of 30 to 45 may have a higher fusion point of the order of 1650 degrees Celsius. But finer grains and impurities in the sand tend to lower the refractoriness by promoting fusion. The impurities that may be found are iron oxide, feldspar and limestone. The strength of the molding sand is also affected by the grain size and shape. Figure 3.25 shows that the green compression strength increases with a decrease in the grain size because the fine grain size provides a large surface area for the binder to act. 3.3 For manufacturing technology, foundry, forming and welding Brahmani river sand 5% bentonite subangular to round grains. GFN equals 54.8. 200. 150. Sand 5% bentonite subangular to round grains. GFN equals 54.8. 200. 150. 100. 50.0123 for 5 moisture percent. Green permeability number 678. GFN equals 78.4. Fig. 3.2 for variation of permeability with grain size Brahmani river sand 5% bentonite subangular to round grains. GFN equals 35.7. 0.08.07.0 6.05.0 4.03.0 2.01000123 for 5 tempering water. Green compression strength MP 67. GFN equals Fig. 3.25 variation of green compression strength. Metal casting processes 3.35. Western bentonite. Bentonite. Western bentonite. Metal casting Fig. 3.25 variation of green compression strength with sand grain size clay and water. Besides the sand grains, clay and water have large influence on major properties of the molding sands. Figure 3.26 A and B shows the relationship between the green compression strength and water content for various clay percentages in the molding sand. Metal casting processes 3.35. Western bentonite. 0.22. 15. 0.14.1. 4.05. 10%. 15 12 9 8 7 6 5 4 3. Maximum green compression strength. During the sand preparation, clay is uniformly coated around the sand grain. Burn-on increases the chilling effect of the mold and increases glazing. Green compression strength. 3.5 for 5.5. 15 12 9 8 7 6 5. Fig. 3.26 variation of green compression strength with clay and water. As can be seen, there is an optimum amount of water to be used for given clay content to obtain maximum green compression strength. During the sand preparation, clay is uniformly coated around the sand grains. The water then reacts with the clay and forms a linkage of silica water silica, or clay, throughout the molding sand. For this linkage to develop, there is only certain amount of water required, which is specified by the type and amount of clay present. Any additional amount of water increases the plasticity and dry strength Fig. 3.27, but reduces the green compression strength. Strength. There is a maximum limit up to which the green compression strength of a molding sand could be increased, which is shown in Fig. 3.28. It is possible to theoretically calculate the water percentage required to achieve this strength, the details of which are given in references at the end of this chapter. These sands are called clay-saturated sands, and are used to advantage in cast iron and heavy non-ferrous metal foundries. These sands would be able to reduce some of the casting defects such as sand expansion, erosion, cuts, and washes, which are essentially caused by the molding sand expansion. Since such sands have higher green compression strength in the range of 100 to 250 kPa, they are to be rammed properly to develop these properties. 0.7 12 15 10. 8. 4. 0.6. 0.5. 0.4. 0.3. 0.2. 0.1. 0. 3.36. 0.2. 0.15. 0.10. 0.05. 0.05 10%. Green compression strength, MPa. 15. Fig. 3.28 maximum green compression strength obtainable with clay molding procedure. Though the properties of molding sand depend to a great extent on its constituents, the molding procedure also makes a difference. The degree of ramming increases the bulk density, or the mold hardness of the sand, and as shown in Fig. 3.29 it is related to the other properties. Increased ramming increases the strength. The permeability of green sand decreases with the degree of ramming. Figure 3.30 shows that when the degree of ramming rises from 3 to 10 rams, the sand gets compacted and in the process reduces the voids in the sand. 0.3 increased water percent, 0.23%, 3.4%, 3.8%, 4.2%. 0.1. 0.5 1.0 dry compression strength. Green compression strength, MPa increased ramming. 1.5 2.0. 8% bentonite. Fig. 3.29 interrelation between sand properties with various constituents. The natural molding sands are generally used because they are freely available. They contain large amount of clay and therefore the moisture content range is wider. The molds can be prepared easily as not. Metal casting much control is needed. Table 3.13 control. Table 3.1. Much control is needed in the sand preparation. In spite of these advantages, natural sands lack the necessary refractoriness and other desirable properties. To achieve the controlled properties for sands as shown in Table 3.13, it is necessary to prepare molding sands synthetica LLY. The natural sand obtained is thoroughly washed so as to remove as much clay as possible. Table 3.13 control sand test data for various types. Casting mate real deformation clay 220. Medium gray iron. 3.38 manufacturing technology, foundry, forming and welding. And the resultant silica grains are sieved to segregate them into the necessary grain sizes. Then the requisite molding sand is prepared by using proper size silica and bentonite of the required type. The mixture is thoroughly mulled by adding water. Synthetic sands by this method would have had higher refractoriness better and controlled mechanical properties uniform or requisite grain size further. This is well suited for foundry mechanization. Table 3.13 shows some typical sand compositions and properties that are desirable in various casting materials. Additives. A number of materials are added to molding sand such as coal dust, sawdust or wood flour, starch and dextrin, iron oxide and silica flour to improve their molding properties. These materials help in improving the casting quality, shown in Table 3.14, in a number of ways as detailed below. Table 3.1 for different types of molding sand additives used. Additives purpose served molasses cereals ethylene glycol. Enhancement of bench life and resistance to drying out. Iron oxide silica flour hot strength development. Coal dust silica flour surface finish and resistance to metal penetration. Cereal sawdust collapsibility and resistance to expand ion defects. Coal dusted is basically used for providing better surface finish to the castings. This, when comes into contact with the molten metal, would provide a gaseous envelope to keep the molten metal from fusing with the sand, thus providing good surface finish. Sawdust or wood flour. The addition of wood flour, about 1.5% max, to molding sand widens the range of water that can be added to get proper green strength. It reduces the expansion defects while improving the flowability of the molding sand and helps maintain the uniform mold density. Too high wood flour makes the molding sand brittle. Starch and dextrin. These are the organic binding materials used with mold and core sands. These increase resistance to deformation, skin hardness, and expansion defects such as scab. Iron oxide up to 3% max in molding sand improves surface finish, decreases metal penetration, reduces burn-on, increases the chilling effect of the mold. Iron oxide. Sawdust or wood flour. The coal dusted is basically used. Sawdust or wood flour. The addition of wood flour, about 1.5% max, to molding sand widens the range of water that can be added to get proper green strength. It reduces the expansion defects while improving the flowability of the molding sand and helps maintain the uniform mold density. Too high wood flour makes the molding sand brittle. Starch and dextrin. These are the organic binding materials used with mold and core sands. These increase resistance to deformation, skin hardness, and expansion defects such as scab. Iron oxide up to 3% max in molding sand improves surface finish, decreases metal penetration, reduces burn-on, increases the chilling effect of the mold, and increases glazing. With enough iron oxide in combination. Metal casting processes 3.39. With silica flour, mold washes could be avoided. Iron oxide decreases green strength and permeability while improving the hot strength. It reduces collapsibility and makes the shake out of the mold difficult. 3.3.5 Indian sands. The normal practice of Indian foundries is to use the locally available river sand. For example, the foundries in Jamshedpur use the local Swarnareka river sand. The river sands normally are of medium to fine grain and sub-angular in shape. They contain about 80 to 85% silica, and the rest are alumina and other impurities. A brief description of the properties of various sands analyzed by National Metallurgical Laboratory is presented in Table 3.15. Rajkot, Kanpur 4.8, Guntur. High silica sands which are normally used by steel foundries are available from Rajmahal Sand, Bihar, Quartzitic Sand, Jamshedpur, Allahabad, Jabalpur, Hyderabad, Madras and Vengurla, Maharashtra. Many of these sands contain very small amounts of clay, and grains are generally of the requisite grade. The typical properties and uses of these sands are presented in Table 3.40 Manufacturing Tech 0.10 Asterisk where A equals angular grains, B equals subangular grains, and C equals round grains. The change in permeability that can be achieved by means of washing is presented in Fig. 3.33, where the permeability of the Rajkot sand is improved by the washing of the clay and adding the 3% bentonite. The bentonite deposits suitable for foundry use are found in Bihar, Kashmir, and Rajasthan. Both sodium bentonite and calcium bentonite are available. These bentonites are light green in color and primarily with sodium base. Rajasthan bentonite can be used for light and medium steel castings, while those found in Bihar can be used for gray iron and steel castings. Comparative properties of Rajasthan and Bihar bentonites, as they affect the Rajmahal sand, are presented in Fig. 3.34. For a detailed description of the composition of the various Indian sands, clays, and their properties, reference may be made to the NML book. 3.3.6 Other sands. Though molding sands are the prime mold materials used in a foundry, there are a number of other materials which are also used for a number of specific properties. 3.42 200 100 00123 45678 Rajkot sand, natural sand, GFN Metal casting processes 3.43 Facing sand. This sand is used next to the pattern to obtain cleaner and smoother casting surfaces. Generally, sea coal or coal dust, finely divided bituminous coal of 2 to 8%, is mixed with the system sand to improve the moldability and surface finish. The sea coal, being carbonaceous, will slowly burn due to the heat from the molten metal and give off small amounts of reducing gases. This creates a small gas pressure in the surroundings of the cavity that molten metal is prevented from entering into the silica grains or fuse with them. This helps in generating good casting surface and also lets the molding sand peel off from the casting during shakeout. Mold wash. Purely carbonaceous materials such as sea coal, finely powdered graphite, or proprietary compounds are also applied onto the mold cavity after the pattern is withdrawn. This is called the mold wash and is done by spraying, swabbing, or painting in the form of a wet paste. These are used essentially for the following REA. Sons, I, to prevent metal penetration into the sand grains and thus ensuring a good casting finish, and 2, to avoid mold-metal interaction and prevent sand fusion. For depositing the mold wash, either water or alcohol can be used as a carrier. But because of the problem of getting the water out of the mold, alcohol is preferred as a carrier. The proprietary washes are available in powder, paste, or liquid form. The powder needs to be first prepared and applied, whereas the paste and liquid can be straight away applied. Backing sand. This is normally the reconditioned foundry sand, and is used for ramming the bulk of the molding flask. The molding flask is completely filled with backing sand after the pattern is covered with a thin layer of facing sand. Since the casting is not affected to any great extent by the backing sand, it usually contains the burnt facing sand, molding sand, and clay. Parting sand. This is the material which is sprinkled on the pattern and to the parting surfaces of the mold halves before they are prepared to prevent the adherence of the molding sand. This helps in easy withdrawal of the pattern and easier separation of the cope and drag flasks at parting surface. It is entirely a non-sticky material such as washed silica grains. This is the material. Sons, I, to prevent pure mold wash. Purely carbonaceous materials such as sea coal, finely powdered graphite, or proprietary compounds are also applied onto the mold cavity after the pattern is withdrawn. This is called the mold wash and is done by spraying, swabbing, or painting in the form of a wet paste. These are used essentially for the following REA. Sons, I, to prevent metal penetration into the sand grains and thus ensuring a good casting finish, and 2, to avoid mold-metal interaction and prevent sand. Backing sand. This is normally the reconditioned foundry. This is the material. 3.3.7 Fluidity. The term fluidity is normally used in a foundry to designate the casting material's ability to fill the mold cavity. The fluidity therefore is a complex property, and there are a number of variables affecting it. Fluidity depends on the casting material as well as the mold. The properties of casting material affecting the fluidity to a great extent are viscosity of the melt, heat content of the melt, surface tension, freezing range, and specific weight of the liquid metal. Lower the coefficient of viscosity of the molten metal, higher would be the fluidity since the melt will be able to flow freely. Since the heat content and superheat of the molten metal decrease the coefficient of viscosity, it would also be responsible for an increase in the fluidity. Similarly, lower surface tension, which promotes wetting of the mold by the melt, would quickly fill the mold, particularly the narrow sections. In general, the alloys with a narrow freezing range have a higher fluidity compared to the wide freezing range ones. In wide freezing range alloys, during the process of solidification, the dendrites are spread over a much larger part of the mold and thus reduce the flow of the metal, decreasing the fluidity. 3.4 For manufacturing technology, foundry, forming, and welding. The mold properties that affect the fluidity are the mal characteristics, permeability, and the mold cavity surface. The way in which heat is transferred by the mold from the melt affects the ability of the melt to fill the mold cavity. For example, in a green sand mold the fluidity would be lower since more heat is extracted by it than in a dry sand mold. The fluidity of a mold, which is coated with refractory washes, would be high compared to the one with no coatings. Similarly, a higher permeable mold is conducive to better fluidity. Fluidity tests. Since fluidity depends on such a large number of diverse variables, it is not feasible theoretically to determine it, and therefore, practical testing is resorted to. The most commonly used testing is the spiral fluidity test. The mold of the same composition that is to be used is prepared with the standard spiral pattern with gating as shown in Fig. 3.35. The casting prepared from the mold is measured for the fluidity, which is represented by the length of the spiral solidified. 51A. 124 25 44. 25. 25. 51. 12 point. Then the fluidity. Then the fluidity. A modified spiral pattern for gray cast iron is presented in Fig. 3.36. Gray cast iron is the most fluid of all the ferrous alloys. The fluidity of gray cast iron is affected by the composition factor CF, which can be expressed as CF equals %C plus 25 cent% SI plus 50 cent% P. Then the fluidity spiral length in cm can be estimated by means of the following empirical relation. Fluidity, cm equals 37.846 yen cf plus 0.228 yen T 389.6 where T equals pouring temperature, OC. The results obtained by Porter and Rosenthal for the fluidity of gray cast iron as affected by the composition, and the melting temperatures are presented in Fig. 3.37. Since the fluidity is affected by the pouring temperature, and to effect the completion of the mold filling in a reasonable time, the pouring temperatures of the molds are accordingly controlled. The pouring temperature should be a little above the melting temperature of the alloy along with a sufficient enough superheat to account for the cooling of the molten metal from the time it is tapped from the furnace till it is. Metal casting processes 3.45. 94. 51.4. 518. 6. Match plate. 45. Overflow. 2100. 2000. 2000. 2000. 3000. 28. Skin dried mold. 3.3. 3. Though the dry sand, skin dried mold, the baking process, metal casting processes. These are the green sand mold, dry sand molds. These are the green sand molds which are these are the green sand is the green sand mold. In order to produce sound castings, molds are required to have some specific properties. Some of them are, it must be strong enough to withstand the temperature and weight of the molten metal. It must resist the erosive action of the flowing hot metal. It should generate minimum amount of gases as a result of the temperature of the molten metal. It should have good venting capacity to allow the gene-rated gases to completely escape from it. Molds that are used for sand casting may broadly be classified as green sand molds, dry sand molds, skin-dried molds. Green sand molds. Green sand is the molding sand which has been freshly prepared from silica grains, clay, and moisture. In a green sand mold, metal is poured immediately and the castings taken out. These are most commonly used and are adapted for rapid production, whereas the molding flasks are released quickly. They require less floor space as no storage is involved. As the mold is produced, the casting is prepared. Thus it is the least expensive of all. Also the tendency for hot tearing of the castings is less in green sand molds. Mold erosion is common in these types of molds. The permeability of these molds should be properly controlled, otherwise blowholes and gas inclusions are likely to form. Dry sand molds. These are the green sand molds which are completely dried by keeping in an oven from 150 to 350 degrees Celsius for 8 to 48 hours depending on the binders in the molding sand. These molds generally have higher strengths than the green sand mold and are preferred because they are less likely to be damaged during handling. These are generally used for medium to large castings. Better surface finish and dimensional accuracy can be achieved by dry sand mold. The main disadvantages are the likely distortion of the mold caused during metal casting processes 3.47. The baking process, susceptibility to hot tearing of castings and longer production cycles. Also this is more expensive than the green sand mold. Skin-dried mold. Though the dry sand mold is preferable for large molds because of the expense involved, a compromise is achieved by drying only the skin of the mold cavity with which the molten metal comes into contact, instead of the full mold. The skin is normally dried to a depth of 15 to 25 millimeters, using either torches or by simply allowing them to dry in atmosphere. This can also be done in pit molding. However, pouring of metal should be completed immediately after the drying process, such that moisture from the undried portion would not penetrate the dried skin. 3.3.9 Molding machines. Hand molding as described earlier is suitable for small batch production, or for large size castings. However, for production work involving large batches of the same type of casting is to be produced, machine molding is a necessity. In the machine molding, there are basically three methods used for ramming the sand into the molding flasks. They are jolting, squeezing. Sand slinging and jolt molding. The sand is first filled into the flask generally from an overhead hopper, and then it is raised to a certain height, before it is allowed to free fall onto a solid bed plate. The resulting impact forces the sand to get compacted uniformly into the mold. This lifting and dropping process continues repeatedly till the required mold hardness is achieved. This type of ramming is suitable for horizontal surfaces. It is very severe on the molding equipment, and also likely to give rise to uneven packing. The sand at the bottom experiences the highest force, and consequently is packed well compared to the sand in the top layers. In the squeeze ramming, a plate slightly smaller than the inside dimensions of the molding flask is fitted into the flask already filled with the molding sand as shown in Fig. 3.38a. A uniform pressure is applied on the plate by either moving it down or by moving the flask upwards. The resulting force compacts the sand uniformly. The sand next to the plate rams hardest while the sand below is progressively less hard. Hardness achieved is also dependent upon the pressure applied on the squeeze plate. Since the hardness achieved follows contour of the squeeze plate which is in contact with the sand, sometimes the plate is provided with contour as shown in Fig. 3.38b to match the pattern for achieving better uniform hardness of the mold. This type is suitable for small castings and is generally suitable for shallow flasks. It is also possible to use a diaphragm to provide differential ramming force required for the contour of the pattern as shown in Fig. 3.38c. A combination of jolt squeeze machines are more common in view of the more uniform ramming that could be achieved by combining the two methods as described above. Sand slinging is done by throwing sand into the flask rapidly and with great force. This process develops uniformly high mold hardness. The process is very fast and gives high uniform sand ramming. The sand should be uniformly sprayed into the mold by moving the nozzle through the entire area of the flask. Also, it is necessary that the sand be sprayed in layers to achieve uniform hardness. However, the initial cost of the equipment is high compared to the other form of molding machines described above. 3.48 Pattern A, B, C. Diaphragm head. Squeeze plate. Fig. 3.38 Types of squeeze heads used for machine molding: A. Conventional squeeze, B. Profile squeeze head, and C. Diaphragm squeeze. March 3, 10 No-bake molding process. No-bake is a casting process that involves the use of chemical binders, furan or urethane, to bond the molding sand in place of clay normally used in green sand molding. Clay-free silica sand is conveyed to the mold fill station in preparation for filling of the mold. A mixer is then used to thoroughly blend the sand with the chemical binder and a catalyst. As the sand exits the mixer, the binder begins the chemical process of hardening. The chemical mixed sand is then poured into the molding flask that is fitted with the cope/drag pattern plate that is complete with the necessary gating and risering system as designed. Each mold half is then compacted to form a strong and dense mold. After a specified period of time, from as little as 10 SEC to as long as the foundry requires depending upon mold size, the sand mixture hardens, resembling a brick in strength, to form the mold halves and the cope/drag pattern plates are removed. Cores, if required, can also be made using the same process. After the sand has set, a mold wash may be applied. The cores, if required, are set into the drag and the cope is closed over the cores to complete the mold. Pouring of molten metal is done normally and the mold is allowed to cool before shake out. The broken pieces of molded sand during shake out are further broken down until they are close to the sand grain size. The sand can now be either reclaimed for reuse in the casting process or removed for disposal. Advantages. It is possible to get good dimensional tolerances, plus or minus 0.125, 0.375 mm, because of the high strength of the mold. No-bake mold can withstand the metallostatic pressure exerted by the molten metal during casting. Because of the rigidity and tensile strength of no-bake molds, thin sections about 2.5 mm thick can be routinely produced. Also, the draft required is less compared to green sand molding. No-bake mold produces fine surface finishes that can be upgraded further with the mold and core coatings to support special finishing on the cast components such as paint or dressing. Metal casting processes. 3.49 Less skill and labor are required than in conventional sand molding. No-bake process is compatible with practically all types of pattern materials as well as it imparts minimal tooling wear. If needed, inexpensive tooling can be used for casting runs for prototyping. It is possible to pour any ferrous/non-ferrous metals in a no-bake mold. Cores and molds prepared with no-bake process can be stored indefinitely. Most of the no-bake systems have excellent shake-out properties. No-bake molding reduces the opportunity for gas-related defects, as the nitrogen content of most binder systems used minimizes susceptibility to gas porosity. Though this process is adaptable to any volume, it is preferable for low to medium volume production capability. March 3, 11 Plaster molding. Plaster mold casting, also called rubber plaster molding, RPM, is a specialized casting process used for producing non-ferrous, aluminium, and copper-base alloys, castings by pouring liquid metal into molds made of plaster of Paris gypsum. In this process, plaster of Paris, CaSO 4.12 H2O, is mixed with water to form a slurry with additives such as ceramic talc, fiberglass, clay, silica flour, fly ash, etc., with water and then poured over the pattern. The additives are used to enhance the mold properties such as green and dry strength, permeability, and castability. The slurry is allowed to preset to a rubbery consistency which allows it to be stripped from the pattern, but which is sufficiently strong to return to the shape it had when on the pattern. The preset mold is then ignited to burn off the volatile content in the set gel, and baked at about 120 to 260 degrees Celsius. This step results in a hard and rigid mold containing microscopic cracks. Cores can also be made using similar process. Cores, if required, are then placed in the drag half. The cope half is then aligned with the drag half, and locating pins on cope going into the matching pinholes in the cope. This assembling process can be done while the molds are still hot, or after they have cooled to room temperature depending on mold complexity. Dried plaster molds have extremely low permeability of about 1 to 2 AFS. In view of this low permeability, gravity pouring is rarely employed, and a vacuum assist is usually required for the pouring of molds. Advantages. Castings produced by plaster molding have high dimensional accuracy that is comparable to that of the castings made in investment molds. Using plaster molding, a surface finish of the order of 1.25 to 3.25 millimeters can be readily obtained. Complex designs can be obtained by using flexible rubber patterns and utilizing the investment casting techniques. Since plaster has low thermal conductivity, castings cool slowly that will allow thin sections to be cast. Wall thicknesses as low as 0.75 to 1 millimeter can be cast at selected locations. Enhanced mechanical properties can be obtained by appropriately controlling the thermal gradients, while slow cooling minimizes warpage and promotes uniformity of structure. Disadvantages. The process is expensive because of the lengthy processing procedures and the one-time use of the mold materials. Compared to green sand molding, plaster molding requires more equipment. Permeability of plaster molds is inherently low when compared to the sand casting process. 3.50 Manufacturing technology, foundry, forming, and welding. March 3, 12 Pit molding. Pit molding is used for large and heavy castings. Pit molding is used for large and heavy castings weighing up to 150 tons, where using a molding flask for the process becomes almost impossible and too expensive for the amount of handling is concerned. The pit is normally formed in the foundry floor with sand. The pit acts as a drag where the cavity is formed. Pattern is placed in the pit, and the sand is rammed around it to form the drag cavity. A separate cope can then be used above the pit, which will be at the floor level. The cope can be constructed with bricks and normally houses the pouring cup and sprue. Vent pipes will be added into the pit to facilitate the escape of gases. This is a slow process and requires a lot of time to complete the mold. March 3, 13 Loam molding. Loam sand contains many ingredients like fine sand particles, finely ground refractories, clay, graphite, and fiber reinforcements. Loam soils generally have better drainage than clay soils. They retain water easily. Organic matter such as chopped straw is added to the sand to provide good ventilation. Loam molds are generally employed for making large castings without using the expensive full patterns and molding flasks. They use skeleton patterns and sweeps to reduce the cost of patterns. Objects such as large cylinders, chemical pans, large gears, round bottoms, kettles, and other machining parts are produced in loam molding. Big molds are constructed using brick framework that will be lined with loam sand and dried. Sweeps, etc. are used for getting the requisite profile of the casting. March 3, 14 Additive manufacturing for mold preparation. It is possible to use additive manufacturing, AM, to directly produce sand molds without using a pattern. Most of the systems use binder jetting or 3D printing, 3DP, process. This process can be used to directly fabricate sand molds as well as cores by selectively jetting binder into a powder bed of foundry sand. X1 and VoxelJet are the two major manufacturers that provide 3D building machines utilizing different technologies and materials. The molding material used by X1 is common silica sand with different binders depending upon the application, similar to the no-bake process discussed earlier. One of the binders provided by X1 is Furan binder for traditional foundries, so that they do not have to make any changes to their molding procedures. Silicate binder offered by X1 is environment friendly with low gas emissions. X1 also offers phenolic binder that is suited for thin walls similar to shell molding. VoxelJet offers Furan binder with silica sand. Normal for easier integration into existing foundry production. As defined earlier, gating systems refer to all those elements which are connected with the flow of molten metal from the ladle to the mold cavity. The various elements that are connected with a gating system, Fig. 4.1, are pouring basin, sprue base, well runner extension, ingate riser. Pouring basin, 2 runners. Sprue base, open top or bob riser. Open top or bob riser. Ingate. Casting. Fig. 4.1 typical gating system. 4.2 manufacturing technology, foundry, forming, and welding. In this chapter, the functions and the design of the various elements of a gating system will be discussed. Any gating system design should aim at providing a defect-free casting. This can be achieved by making provision for certain requirements while designing the gating system. These are as follows. 1. The mold should be completely filled in the smallest time possible without having to raise the metal temperatures or use higher metal heads. 2. The metal should flow smoothly into the mold without any turbulence. A turbulent metal flow tends to form dross in the mold. 3. Unwanted material such as slag, dross and other mold material should not be allowed to enter the mold cavity. 4. The metal entry into the mold cavity should be properly controlled in such a way that aspiration of the atmospheric air is prevented. 5. A proper thermal gradient be maintained so that the casting is cooled without any shrinkage cavities or distortions. 6. Metal flow should be maintained in such a way that no gating or mold erosion takes place. 7. The gating system should ensure that enough molten metal reaches the mold cavity. 8. The gating system design should be economical and easy to implement and remove after casting solidification. 9. Ultimately, the casting yield should be maximized. To have all these requirements together is a tall order. Still, mold designer should strive to achieve as many of the above objectives as possible. Before going into the mechanics of gating design, let us describe some of the functions and types of the various gating system elements. For point 1.1 elements of a gating system. Pouring basin. The molten metal is not directly poured into the mold cavity because it may cause mold erosion. Molten metal is poured into a pouring basin, which acts as a reservoir from which it moves smoothly into the sprue. The pouring basin is also able to stop the slag from entering the mold cavity by means of a skimmer or skim core, as shown in Fig. 4.2. It holds back the slag and dirt which floats on the top, and only allows the clean metal underneath it into the sprue. The pouring basin may be cut into the coke portion directly, or a separate dry sand pouring basin may be prepared and used as shown in Fig. 4.2. The molten metal in the pouring basin should be full during the pouring operation, otherwise a funnel is likely to form through which atmospheric air and slag may enter the mold cavity. One of the walls of the pouring basin is made inclined at about 45 degrees to the horizontal. The molten metal is poured on this face such that metal momentum is absorbed and vortex formation is avoided. In some special cases, the pouring basin may consist of partitions to allow for the trapping of the slag and maintaining constant metal height in the basin. The main function of a pouring basin is to reduce the momentum of the liquid flowing into the mold by settling first into it. In order that the metal enters into the sprue without any turbulence, it is necessary that the pouring basin be deep enough, and also the entrance into the sprue be a smooth radius of at least 25 millimeters. Experience shows that the pouring basin depth of 2.5 times the sprue entrance diameter is enough for smooth metal flow and to prevent vortex formation, as shown in Fig. 4.3. Gating systems for casting 4.3. Skim core. Cope. A. Green sand, B. Dry sand. Fig. 4.2 pouring basin. Sprue. D. 2.5 D. 25 R. Fig. 4.3 pouring basin proportions. In order that a vortex is not formed during pouring, it is necessary that the pouring basin be kept full. Further provision should be made in the pouring basin so that constant conditions of flow are established. This can be achieved by using a strainer core, as in Fig. 4.4a. A strainer core is a ceramic-coated screen with many small holes. The strainer restricts the flow of metal into the sprue, and thus helps in quick filling of the pouring basin. It helps in providing a smooth flow while restricting the flow of slag into the mold. A ceramic filter as shown in Fig. 4.4b completely stops slag, allowing only clean metal to go into the sprue, and also ensures a constant flow of metal. The metal should be poured steadily into the pouring basin, keeping the lip of the ladle as close as possible. Pouring basins are most desirable with castings in alloys which form troublesome oxide skins, aluminium, bronze, etc. Sprue. Sprue is the channel through which the molten metal is brought into the parting plane, where it enters the runnas and gates to ultimately reach the mold cavity. The molten metal, when moving from top of the cope to the parting plane, gains in velocity, and as a consequence, requires a smaller area of cross-section for the same. 4.4 Manufacturing technology, foundry, forming and welding. Amount of metal to flow at the top. If the sprue were to be straight cylindrical as shown in Fig. 4.5a, then the metal flow would not be full at the bottom, but some low-pressure area would be created around the metal in the sprue. Since the sand mold is permeable, atmospheric air would be breathed into this low-pressure area, which would then be carried to the mold cavity. To eliminate this problem of air aspiration, the sprue is top-aired to gradually reduce the cross-section as it moves away from the top of the cope as shown in Fig. 4.5b. A.B. Fig. 4.4 pouring basin designs with a strainer core, A, and ceramic foam filter, B. Air. A. Straight sprue, B. Tapered. Fig. 4.5 sprue designs, A. Straight, B. Tapered. The exact tapering can be obtained by the equation of continuity. Denoting the top and choke sections of the sprue by the subscripts T and C respectively, we get at Vt equals ACVC. Or TCCTA equals AVV. Since the velocities are proportional to the square of the potential heads, it can be derived from Bernoulli's equation. TCCTA equals AHH. Gating systems for casting 4.5. The square root suggests that the profile of the sprue should be parabolic if exactly done as per the above equation. But making a parabolic sprue is too inconvenient in practice, and therefore, a straight taper is preferable. It has been found in practice that a straight tapered sprue is able to effectively reduce the air aspiration, as well as increase the flow rate, compared to a cylindrical sprue. In order to arrive at the dimensions of the sprue at the top and the subsequent taper, one has to consider the head of the metal in the pouring basin as shown in Fig. 4.6. Metal at the entry of the sprue would be moving with a velocity of 2gh, and hence at equals hth, where h equals actual sprue height, and ht equals h plus h. Table 4.1 shows the theoretical values of area ratios of top and choke portions of the sprue based on sprue height and metal head in the pouring basin. Though these ratios are theoretically correct, often it is not possible to control exactly the amount of the head in the pouring basin during the pouring. Hence, it is a general practice to neglect the effect of the pouring basin head and proportion the sprue top solely based on the sprue height alone. Table 4.1 Theoretical ratios of sprue top and choke areas based on pouring basin depth. Sprue height, mm, depth in pouring basin, mm, 50 100 100 and 50 200 200, and 50 50 1.41 for 1.225 1.155 1.118 1.095 100 1.732 1.41 for. This is a reservoir for metal at the bottom of the sprue, to reduce the momentum of the molten metal. The molten metal as it moves down the sprue gains in velocity, some of which is lost in the sprue base well by which the mold erosion is reduced. This molten metal then changes direction and flows into the runners in a more uniform way. Reasonable proportions for a sprue base well are presented in Fig. 4.7. A general guideline could be that the sprue base well area should be 5 times that of the sprue choke area, and the well depth should be approximately equal to that of the runner. For a narrow and deep runner, the well diameter should be 2.5 times the width of the runner in a 2-runner system, and twice its width in a 1-runner system. H. Cope drag. HT. PL. Fig. 4.6 Sprue proportions. 4.6 Manufacturing technology, foundry, forming and welding. W. D. Area equals UB. 2.5 W. 2.5 W. Equals WD/2. Area equals 2 AB. Fig. 4.7 Sprue base well design. Runner. It is generally located in the horizontal plane, parting plane, which connects the sprue to its ingates, thus allowing the metal to enter the mold cavity. The runners are normally made trapezoidal in cross-section. It is a general practice for ferrous metals to cut the runners in the cope and the ingates in the drag. The main reason for this is to trap the slag and dross, which are lighter and thus trapped in the upper portion of the runners. For effective trapping of the slag, runners should flow full as shown in Fig. 4.8a. When the amount of molten metal coming from the down sprue is more than the amount flowing through the ingates, the runner would always be full, and thus slag trapping would take place. But when the metal flowing through the ingates is more than that flowing through the runners, then the runner would be filled only partially as shown in Fig. 4.8b, and the slag would then enter the mold cavity. Slag runner. A. Runner full, B. Runner partially full. Slag runner. Fig. 4.8 runner, A. Full runner, B. Runner partially full. Runner extension. The runner is extended a little further after it encounters the ingate. This extension is provided to trap the slag in the molten metal. The metal initially comes along with the slag, floating at the top of the ladle, and flows straight going beyond the ingate, and then trapped in the runner extension. Gating systems for casting. 4.7. 4.1.2 Gates or ingates. These are the openings through which the molten metal enters the mold cavity. The shape in the cross-section of the ingate should be such that it can readily be broken off after casting solidification, and also that it allows the metal to enter quietly into the mold cavity. Depending on the application, various types of gates are used in the casting design. They are the following. Top gate. This is the type of gating through which the molten metal enters the mold cavity from the top as shown in Fig. 4.9. Since the first metal entering the gate reaches the bottom, and hotter metal is at the top, a favorable temperature gradient towards the gate is achieved. Also, the mold is filled very quickly. But as the metal falls directly into the mold cavity through a height, it is likely to cause mold erosion. Also, because it causes turbulence in the mold cavity, it is prone to form dross, and as such the top gate is not advisable for those materials which are likely to form excessive dross. It is not suggested for non-ferrous materials and is suggested only for ferrous alloys. It is suitable only for simple casting shapes, which are essentially shallow in nature. To reduce the mold erosion, pencil gates Fig. 4.9a are provided in the pouring cup. This type of gate requires minimum of additional runners to lead the liquid metal into the cavity, and as such provides higher casting yield. Capabilities of top gating system are significantly extended by using direct pour top gating system, incorporating insulating sleeve with a ceramic foam filter as shown in Fig. 4.9b. Pouring cup strainer core. PL mold cavity cope drag. Insulating sleeve. Ceramic filter. Cope drag PL. Mold cavity. A-B. Fig. 4.9 top gate. Bottom gate. When molten metal enters the mold cavity slowly as shown in Fig. 4.10, it would not cause any mold erosion. The bottom gate is generally used for very deep molds. It takes somewhat higher time for the filling of the mold. These gates may cause unfavorable temperature gradients compared to the top gating. Thus, the system may have to use additional padding of sections towards risers, and large riser sizes to compensate for the unfavorable temperature distribution. Bottom gating may sometimes be preferable in conjunction with the use of side risers, since the metal enters the riser directly without going through the mold cavity. 4.8 Manufacturing technology, foundry, forming and welding. Casting. Sprue. Pouring basin. Ingate. Runner. Runner extension. Sprue base well. Fig. 4.10 bottom gate. Parting gate. This is the most widely used gate in sand castings. As the name implies, the metal enters the mold at the parting plane, when part of the casting is in the cope and part is in the drag as in Fig. 4.11. For the mold cavity in the drag, it is a top gate, and for the cavity in cope, it is a bottom gate. Thus, this type of gating tries to derive the best of both the types of gates, viz. top and bottom gates. Of all the gates, this is also the easiest and most economical in preparation. However, if the drag portion of the mold cavity is deep, it is likely to cause mold erosion and aggravate dross formation and air entrapment in the case of non-ferrous alloys. This can be somewhat reduced by making the gate area large such that the liquid metal velocity is minimized, and it flows slowly along the walls into the mold cavity. P mold cavity L cope drag. Fig. 4.11 parting gate. Gating systems for casting 4.9. Step gate. Such gates are used for heavy and large castings. The molten metal enters Fig. 4.12 mold cavity through a number of ingates, which are arranged in vertical steps. The size of ingates are normally increased from top to bottom such that metal enters the mold cavity from the bottommost gate, and then progressively moves to the higher gates. This ensures a gradual filling of the mold without any mold erosion and produces a sound casting. In designing a casting, it is essential to choose a suitable gate, considering the casting material, casting shape and size so as to produce a sound casting. Mold cavity. Pouring basin. PL. Cope. Drag. Fig. 4.12 step gate. Riser. Most foundry alloys shrink during solidification. Table 4.2 shows the various volumetric shrinkages for typical materials. As a result of this volumetric shrinkage during solidification, voids are likely to form in the castings, as shown in Fig. 4.13, unless additional molten metal is fed into these places, which are termed hot spots, since they remain hot till the end. Hence, a reservoir of molten metal is to be maintained from which the metal can flow readily into the casting when the need arises. These reservoirs are called risers. As shown in Table 4.2, different materials have different shrinkages, and hence the risering requirements vary for the materials. In gray cast iron, because of graphitization during solidification, there may be an increase in volume sometimes. This of course depends on the degree of graphitization in gray cast iron, which is controlled by the silicon content. In order to make them effective, the risers should be designed keeping the following in mind. The metal in the riser should solidify in the end. The riser volume should be sufficient for compensating the shrinkage in the casting. 4.10 Manufacturing technology, foundry, forming and welding. Table. Material shrink. Void shrinkage. Fig. 4.1. In order to satisfy the above requirements, risers of large diameters are generally used. But it proves to be a very expensive solution since the solidified metal in the riser is to be cut off from the main casting, and is to be melted for reuse. Higher the riser volume, lower is the casting yield, and as such it is very uneconomical. The risers are normally of the following types: top risers which are open to the atmosphere, blind risers which are completely concealed inside the mold cavity itself, and internal risers which are enclosed on all sides by the casting. Gating systems for casting 4.11. The top riser is the most conventional and convenient to make. But the position where it can be placed is limited. The top being open loses heat to the atmosphere by radiation and convection. To reduce this, often insulation is provided on the top such as plaster of Paris, asbestos sheet, etc. The blind riser, since it is surrounded by the molding sand, would lose heat slowly and thus would be more effective. Also, it can be located more conveniently than an open riser. The best is the internal riser, which is surrounded on all sides by the casting such that heat from the casting keeps the metal in the riser hot for a longer time. These are normally used for castings, which are cylindrically shaped or have a hollow cylindrical portion. Chill. In a casting, metallic chills are used in order to provide progressive solidification or to avoid the shrinkage cavities. Chills are essentially large heat sinks. Whenever it is not possible to provide a riser for a part of the casting which is heavy, a chill is placed close to it as shown in Fig. 4.14, so that more heat is quickly absorbed by the chill from the larger mass, making the cooling rate equal to that of the thin sections. Thus, this does not permit the formation of a shrinkage cavity. But use of a chill essentially means providing higher cooling rate, which is also likely to form a hard spot at the contact area with the chill, and may, therefore, cause a problem if that areas need further processing by way of machining. 4.1.3 Casting yield. All the metal that is used while pouring is not finally ending up as a casting. Typical routes the metal would take in a foundry are shown in Fig. 4.15. There will be some losses in the melting.